From the white CTLE video, we know a good equalization EQ must be a good inverse transfer curve of the channel, especially at a high frequency or data rate. Could you tell me why we imply that? First, the high data rate may have a very tiny eye-opening margin to begin with. For example, the 32 gigabit per second only has 31.25 picosecond bit period, and the 1 gigabit per second has 1 nanosecond bit period. If the residual eye width after the EQ is 50% UI for both data rates, that's clear. The 32 gigabit per second eye width has less than 16 picosecond margin for other total link budget, and 1 gigabit per second eye width still has 500 picosecond without any concern. Also, if the channel in PCB or cable is the same or similar, the insertion loss is scaled with the data rate or frequency. Therefore, we only focus on the high frequency LFEQ. But does that make sense to everyone? Yes or no? For the PCB backplan, the loss the scale with the data rate, and it's likely that we don't change the PCB backplan during the data switching. Could you imagine you keep changing the backplane on the server from 56 gigabit per second, jumping back to 10 gigabit per second? Of course not, but it's likely you may disconnect the cable and try to connect to another different cable. For example, you may have an expensive cable for 20 gigabit per second with a 20 dB loss, but you could swap a cheap cable for the 1.62 gigabit per second operation. Unfortunately, the cheap cable may have a high insertion loss up to 12 dB at 800 MHz. Furthermore, the cable's insertion loss may not scale well from high frequency back to the low frequencies because of the skin effect. As you can see, the curve gain at low frequencies because of the skin effect isn't the same frequency response of the straight line at the high frequencies caused by the dielectric loss. So, we must pay attention back to the low frequency loss of any cable, not because the loss is small and can be negligible anymore. Everyone may be wondering if the channel loss is big at low frequency based on my previous comment. Here you go. From the DisplayPort DP insertion loss of the reference cable, the channel loss is roughly 13 dB from 1.62 gigabit per second to 2.7 gigabit per second, and 21 dB from 5.4 gigabit per second to 20 gigabit per second. You should already notice that the channel loss could be constant over a very wide frequency range and not scale with the frequencies from DP's specification. Besides the DP protocol, you might say you don't need the LFEQ for other SerDes standards. Is that true? Of course not, unless your SerDes only target a single data rate of a single protocol. Instead, you might want to design a multi-protocol SerDes for multiple usage in your existing projects or even future projects. Therefore, you may need to target different data rates and different channel loss. In addition, the LFEQ may only provide a more flexible frequency response, which will better fit the inverse of the channel's frequency response than the high frequency EQ of the CTLE only. to show how the LFEQ improves the EQ performance, we provide a few case studies from the industry, and hopefully that's clear to you why you need the LFEQ. Then your next question will be how to design the LFEQ. Is that easy? As we mentioned in the Why TX FFE and Why DFE videos, both EQ have a more flexibility to fit the channel's frequency response well and cancel the ISI effectively. So, can we start to apply for the TX FFE? Unfortunately, that cannot be done with the TX FFE. Could you tell me why not? Correct. The TX is very power hungry, and the most popular number of taps in the specification is only 3 for power saving. Then the 3 UI information cannot cover very low frequency information over EQ ability for sure. Then you might ask for the DFE, which usually has many more taps to even cancel the signal reflection from the package or any discontinuity. Does that work? Well, the maximum number of taps I've seen is 36, which should not only cost much more power than it should be, but it also cannot achieve the LFEQ peaking frequency at as low as possible. If that's the case, we know the CTLE might be able to equalize the low frequency loss as low as possible from Why CTLE video. Can we apply for it? Before answering, let's dive into the source degradation CTLE topology. As you can see, the RD12 is the resistive load, and the CP will be the parasitic associated with the device capacitance. The RS/CS of the input differential pair M1 M2 sets the pole and zero of the frequency response. Before diving into the equation, let's intuitively look at the frequency response. At the DC or very low frequency, the CS is open and the pair RC network is dominated by the RS, so the DC gain drops. On the other hand, at a high frequency, the RS impedance is much larger than the 1 divided by omega CS. So the pair RC network is dominated by the CS, and the gain is higher to achieve the high pass characteristic. Of course, because of the output pole dominated by the RD, CP, and the bandwidth is dominated by the RC time constant. Please be advised that the slope of the high pass response of the CTLE is fixed and only move the zero frequency by the RS/CS time constant without too much flexibility. Therefore, we can only apply the traditional source degradation CTLE only for the high frequency equalization, not the LFEQ. Make sense? If yes, we need a second building block, at least a second path. I guess the most popular and intuitive way to add the second path for the LFEQ is the negative loop. What do I mean? From a simple frequency response, we can reduce the DC gain to achieve the high pass frequency response. Also, if the zero frequency can be as low as possible, then the LFEQ is simply down. Also, to reduce the DC gain, we could just apply the output of the HFEQ CTLE to a low pass amplifier, subtracting the feedback from the CTLE's input Intuitively, the block diagram of this low-pass negative feedback path may realize your desired image of the LFEQ frequency response. Besides this negative feedback topology, do you have other options? Bingo! In addition to the negative feedback, I think you may be familiar with the feed-forward path as we mentioned in the TX FFE video. The only difference in the TX FFE's EQ is to apply the discrete time to implement the de-emphasis or reduce the DC or low frequencies energy. This is much easy and efficient to do the delay in the digital domain through the flip-flops and the RX input in a continuous time domain. We still can apply the same feed-forward equation FFE to de-emphasize the DC or low frequency gain easily. Since it's at the continuous time domain, we can make the cutoff frequency as low as possible by reducing the RC bandwidth or the GM effectively. Along with the high frequency CTLE, the two-path summing scheme, the first path realizing high frequency peaking with the degenerated small RC, and the slow path using a large RC low-pass filter in front, which obtain low frequency peaking after being subtracted from the fast path without impairing the RX input return loss or signal integrity. Since both peaking strengths are independently programmable, the total equation can be tuned precisely or flexibly at high frequency and low frequency to match the insertion loss of any channel profile. After both understanding why you need the LFEQ and how to design it, you may appreciate how the LFEQ helps the total EQ frequency response nicely. For example, without the LFEQ, there's a dip at the mid or low frequency band of the total frequency response. Fortunately, the LFEQ helps compensate for the loss dip at the mid or low frequency band to have a maximum flat bandwidth up to or beyond the next rate of the data rate. Therefore, in the time domain, you can see the LFEQ helps reduce the long tail of the pulse response quite a bit compared to the residual long tail without the LFEQ. From the eye diagram, in the eye height over eye width of the NRZ or PAM430 system, both references show the LFEQ can improve the eye opening at the input of their sampler. Hopefully, those industry demonstrate a real improvement in addition to my mental model in the circuit image. In the past, we always emphasize the equation EQ at high data rate since the insertion loss scale over frequencies in a fixed backplane channel. Then the loss should be much smaller at a low frequency, which might not apply to the cable, which could be replaced with different insertion loss over time. So it's possible to have a very cheap cable having a very high insertion loss at low frequency. Therefore, DP does define the reference loss at low data rate with loss greater than the 12 dB, which is not small anymore, not to mention a low cost or cheap package substrate in the link. Since we talk about the cable, we also show that a few cables skin effect at low frequency would have a greater loss than the high frequency scale due to the dielectric loss. Therefore, the LFEQ can provide the extra non-scaled curve loss to remove more residual ISI. As we know, the LFEQ can help equalize the channel more precisely, not only over the wide frequency range of the DP, but also over other multi-protocol SerDes over different channels, since such LFEQ can cancel long-tail ISI. The discrete time EQ like the TX FFE or RX DFE don't be the LFEQ. Instead, the CTLE could be the LFEQ, but the traditional source degradation CTLE may not have the flexibility to change the EQ slope at different frequency. Therefore, we must add the second path for the LFEQ, either from the negative feedback or the feedforward path to achieve the piecewise linear frequency response to be a more precise inverse of the channel's loss profile. Lastly, thanks to people who share their LFEQ implementation in their SerDes product, no matter the NRZ or painful SerDes does show a very open eye after adding the LFEQ. Hopefully, the second result to show you the LFEQ is handy in the industry, in addition to my personal mental model image. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. And please share your comments down below. Lastly, please share the video link with the people who may be back from